regression and correlation, we're trying to see if two things are related in some way. So let's use the example, and this is kind of a weird example, but let's use the example of buying candy. Let's say there's a child and he has a certain amount of dollars and he goes in to buy candy. Now for the simplicity of this, let's say one gummy bear is $1. So if you have $0, you can't get any gummy bears. You get 0 gummy bears. But if you have $1, you can get 1 gummy bear. And of course, if you have $5, you can get 5 gummy bears. And if you have $2, you get 2 gummy bears, $3, 3 gummy bears, $4, 4 gummy bears. Now, that's pretty obvious. But that's really what regression is. We're seeing how one thing changes with the other. So we can draw a line between these. So what we could say is that as we increase $1, we get 1 extra gummy bear. So we're increasing $1, we get 1 extra gummy bear. That's the essential idea of what regression is. We're trying to see if we can predict our y variable from our x variable. And here it's very explicit. We really can do that. Now, with that last example, it's very explicit what's happening. And because it's really determined, if you have $1, you get a gummy bear. If you have $1.50, you still only get 1 gummy bear because you can't afford 2. In science, and when we're talking about data, it's not quite that simple of a relationship. So one example is age and height. Generally, as we get older, we're going to increase in height. Let's talk about adolescents or children. Let's say anywhere from 0 or newborn to, 15 years old. What we expect is generally as we increase in age, we increase in height. I'm not going to talk about, specific age-related things like puberty where, you get a growth spurt and stuff like that. Let's just really just talk about a linear relationship here. However, that's not always the same change for people. So some people might fall in this line, but maybe some people are just taller than other people. Even at early ages, they're still a bit taller than this line. But other people are not as tall, so some people are shorter, so they're going to be below this line. This line is really just an average of height at each age. And that's one way you can think about regression. So at this age specifically, this is the average height. And some people are below it, and some people are above it, and some people are on it. But the idea is we start to get data points around this line. But what we can see here is even though there's some people that are below and some people that are above this line, more or less people are increasing in height as they increase in age. So we do get a pretty strong relationship. And that's what we call our regression, is this red line here. But then we need to talk about correlation. And correlation is really how well that line fits our data. So in the gummy bear and dollar example, the regression line fit our data perfectly because we knew exactly how much money you needed to get how many gummy bears. But because data is less determined, we do find that our data is going to be a lot more variable. And so here, this red line does do a good job of predicting our data, so we could get a good idea of what height you would be depending on your age, but we do see differences. For example, this point here is that far from the mean at that age. And so this one is that far below it. And this one is that far above it, and that one's that far below it, and so forth. So what a correlation is really the distance between these dots and this line. Now in a past video, I talked about standard deviation in this same way. If we have a mean, our scores can be below the mean. So if our mean is 10, for example, they could be a score of 6 would be back here, and some could be above the mean. A score of, let's say, 12 would be around here, and so forth. And what we did in that video, I'm not going to spend too much time here, what we did in that video is we determined how far people were from this mean, and we called those deviations, and we calculated standard deviation from that. And if you don't remember that video, or if you haven't seen it, check it out. But essentially what we determined was that standard deviation, conceptually, not literally, but conceptually, is the average distance people are from this line. Now correlation is the same thing, but now our line is just tilted. But that's still fine, because what we're going to do is correlation, conceptually again, is how well these dots lay onto this line. So if they're very far from the line, for example, out here and out here, that means our correlation is not very good. What that means is that this line isn't doing a good job predicting these 2 points, for example. But it is doing a good job on the majority of the points. But the more we get points all over the place, further away from the line, our correlation decreases. So a correlation goes from -1 to 1. -1 means that it's a negative correlation. So here we have a positive correlation. As we increase in age, we increase in height. A negative correlation would be as we increase in age, we decrease in height. So you can maybe picture, I don't know how scientifically true this is, but when you're elderly, you lose height, maybe? I'm not too sure. But we could think of it that way. So as you get more and more elderly, you lose height more and more. And that's a negative relationship. And then we're going to just see how well the dots plot onto this line instead for that negative relationship. So if we have this regression line here, with this regression line, we could talk about different correlations. So let's say we have these data points here. What we see is that the distance between these data points in the line are fairly small. They're pretty much all on this line. So what I would do is I would call that a high correlation, or possibly a correlation of something like, let's say 0.90. So it's high because it's getting closer to 1. Now we could also have a high negative correlation if we look at it like this, with the same kind of, the points with the same kind of distance. So there's a small distance between these points and the line. And what we would call that is a high negative correlation. For example, 0.90, but negative. So the negative and positive sign is just the direction of this line. So before positive was going upwards, now it's going downwards to make it negative. But regardless, the points are really close to the line, so we have a high correlation. So it's close to either -1 or +1. If our points are instead far from the lines, we have lots of different points far from the line like this, what we're seeing is that this line doesn't well predict our data. So I can ask you, if I give you an age of, let's say, something like 15, what might my height be? Well, really, if we're looking around 15, it could be anywhere from down here to maybe up here. That's quite the different range. And that's really what we're saying here. Even if there is a relationship between height and age, we want to know how confident we are with that relationship. So we might see this as a correlation of 0.10. So really, correlation just has to do with the idea of how good or how confident we are at predicting our y variable from our x variable. So with this one, I wouldn't be very confident, just because even though we have this positive relationship between the two, our data doesn't really follow that line very strictly. Now with a more highly correlated relationship, this line is doing a much better job at predicting our data. So if someone asks me what would someone's height be at age 15, I do have a pretty good predictor of what that might be. So it's a small range here. I'd say something like, from this to this. And that's what the high correlation means, is that we're going to have all our points near this regression line, which means that a regression line is actually a good predictor of our data. What I mean by that is that age can really tell us a lot about height, where if our correlation is low, so near 0, then our age can't tell us very much about height. And so the idea is that a regression line is going to tell us what that relationship is. So one increase in age is how much increase in height. But then our correlation is going to tell us, well, how well does our data fit that line? Now, this is getting a little bit further than you probably need to at this point, but it's important to understand that not all relationships are linear. And what I mean by linear is a straight line. So as one thing increases, the other thing increases or decreases. But sometimes we have a relationship where we call it curvilinear. So it's not just a linear line, but it's a curved line. And what I mean by that is I'd like to use this example, alcohol. Because what happens is alcohol, when you have a bit of alcohol, we become more social people on average. So as we drink more alcohol, let's just do it like this, we're going to increase how social we are. Up to a point though, because after a point, you're starting to get maybe too inebriated and you start losing sociability because you have less cognitive ability, because we know that alcohol does reduce cognitive ability. So at first, maybe it's reducing your inhibitions and making you more, let's say, brave. But then eventually you're losing your ability to communicate effectively. And what happens is that your sociability decreases. So this is when you're having a couple drinks and you're starting to get, relaxed and social. Then you have too many drinks and then you're losing that sociability because you're, unable to really comprehend your environment. Maybe you're not feeling so well, and so you lose this sociability until you can't really communicate with people at all. Now what this really looks like is a line like this. So it doesn't matter, but we call this a quadratic line. And what that means is it increases until it decreases. And a correlation, again, just has to do with how well our regression line, so this is a different kind of regression line, a quadratic regression line. And a correlation is how well our regression line fits our data. So if our data is like this, we find that this regression line does do a very good job at predicting our data, because if we look at how far all the data points are, we see that the data points lie pretty close to this regression line. But if we instead wanted to predict alcohol from sociability with a linear regression, so basically with the hypothesis that the more alcohol you drink, the more social you are, you would have this regression line. Then we could map and see that this one might be right on it, but then what happens is our correlation is dramatically smaller because so many points are far away from that regression line. So whereas these points fit this quadratic regression really well, they don't fit this linear regression well at all. So the point there is a correlation is just how close our dots are, our data points are, to a regression line. And we have different regression lines that we can use, which will change our correlation as we see here. And then the correlation is how confident we are with that relationship that we've determined. So here, I'd be very confident with this quadratic red regression line because I know, based on my data, because it fits this line so well, that as you drink, your sociability increases up to a point, then it decreases. But I wouldn't be confident with this linear regression where it doesn't fit the data very well at all. And so I know that as you increase alcohol, it doesn't just keep increasing your sociability.